This video, we're going to talk about kinetics, both reaction rates and an intro to rate loss. So take out your notes, get started so we can start doing the problem sets, and hopefully you will find this video informative. All right, so what is this? What is kinetics and how does it apply to overall concentration? In kinetics, what we do is we try to find out how fast reactions are going to occur. And the rate of reaction for any sort of chemical reaction usually has a couple of characteristics. The first one being that the rate of disappearance of a reactant can be measured. So if you think about, for example, two reactions, and I have a product and I have a reactant. How fast are those reactants being used? I can actually measure that rate. The second one has to do with the rate of the appearance. So as you move forward in the equation, you're going to get a lot of product being produced. However, if you take a look at your reactant, you could see also that that's going to be connected to that. And the last one is how fast the whole reaction is proceeding. And usually what you're going to be looking at is concentration and how that changes over time from reactants to products. And so when you're thinking about reactions, I want you to really think about this idea of rates or speed in terms of time and looking at concentration. So in terms of kinetics, let's take a look at this equation here. A plus B yields D plus E. If I want to find out how fast A is being used, what I use is the negative delta A over delta T, which tells me it's a negative sign because basically that means I'm consuming that. But the negative sign is needed as rates are always positive values. So even though we're expressing rate as a negative sign, we're always going to be expressing total rate as positive because obviously we're looking at, moving forward in terms of time. However, for a product, what you're going to get is delta D over T, which means that that's going to have its individual rate depending on how fast you're moving and producing your product. So just make sure you write this one down about rate versus product versus reactant. Now in kinetics, we usually talk about how they're connected with each other. So if I take a look at this equation, A plus B yields D, D, and E, what you can see here is we're going to be using the coefficient for each one to determine how fast the other one's going. So they're all going to be proportional to each other. And the way we're going to use that is we're going to use the coefficients and dividing that coefficient by 1, or 1 divided by the coefficient, to multiply by the rate. And that's going to equal to the other rate, either consumption or production. So if I want to know what the B is in this case, or the rate of B, all I need to do is find the equation and then find out what the rate for A is and use A's coefficient, which is going to be this. And also, if I wanted to find out what the product production is, I can also use 1 to find the other. So as you can see from here, all these rates are going to be connected because you can always find out when one is being consumed, how much you're producing the other one using this ratio. Now here's an example of concentration over time, and as you can see from here, you can calculate the instantaneous rate by looking at the slope of a tangent line. So if you draw a tangent line right here, right through it, you find that equation, your slope of that tangent would be at that point where they go ahead and touch. So you would actually find the rate at which that slope is going to have, and you obviously need an equation for that line to determine that instantaneous rate. And you can do that on the computer or you can do that later on. But the idea here is that if I want to find out what the rate is for each point on that line, what I would have to do is start drawing these tangent points. And as an example, as NO is being produced, at some point the NO value is going to stay flat because the concentration of NO is going to be stable as the amount of N2 gets consumed. Now, conversely, what you're also seeing here is NO and NO2 are also going to share the same rate. But O2 is being produced half as fast. And so we can tell from this because of the mole ratio. So the mole ratio of NO2 to 2NO is equal to 2 to 2. However, for O2, it's going to be half. And by looking at how NO2 is being produced, you can also determine the speed of each one. So taking a look at this reaction, we can see that NO2 is a drop. And NO and O2 is going to be an increase. However, for O2, as you can see from here, it's going to be half as fast because you only have, for every 2 moles of NO2, you're going to get 1 mole of the O2. Now, putting along this concept, let's take a look at this equation. 2a yields a squared plus b squared. Over time, what's going to happen is if you're producing a certain amount of product, let's assume it's going to be, in other words, A2 and B2, what you're starting to see is that if you fast forward to 60 seconds, you're going to find that the AB concentration is going to decrease. And because it's decreasing, you're going to get a production of A2 and B2. And so if I want to know exactly what the rate of this would be, I can go ahead and determine that by looking at what happens between time 0 and time 60. So here's an example of that equation. If I take a look at AB production, what I can see is that if I take a look at the final and the initial, you take 5 molar of AB versus the initial, which is 15, you subtract it, you're going to get negative 10. Then you divide it by that 60. However, the whole thing is going to be positive value because we always express rates as being a positive value for that. So your concentration here would be, your rate would be molar per second. Now, in terms of the appearance of A2, this would actually work the same idea. You're going to take the 5 molar, subtract it by 0.00 molar, and you're going to get 5 molar over 60. And in this case, you're going to calculate your rate to being 0.0833. So again, looking at this idea of final minus initial, dividing it by the time. And if I want to find out what the rate is for A or A squared or AB, what I would find is that you can actually use the mole fractions here, the 1 over 2, multiply by the rate of, let's say, A2, and then you would end up finding rate of AB by multiplying those out. So again, you can always going back and forth in terms of the rates based off what you have. Okay, that brings us to our next one, which is going to be the rate law. Now, rate law is a way to write the overall equation in terms of both the concentration of A and B of the reactant side and take a look at what these exponents are going to be. So if I take a look at rate of disappearance of reactants, what I can see here is that your rate is going to be your overall speed for that reaction, and K is going to be that constant. However, if you take a look at your reaction orders, what they call them, these are going to be your exponents. So reaction order for M, reaction order for N would indicate how fast these reactions would be going relative to each one. So here are your 3 types of reaction orders, and make sure you guys know and write down what they are. They're going to be 0, first, and second order. And 0 order is going to be a 0 exponent, first order is going to be a 1 exponent, and 2 is going to be a second exponent. Now the most important thing is that these can only be found in experimental data, which means that you cannot get the rate orders any other way unless you take a look at a tabulated form of information. Alright, so 0 order reaction revolves around this idea of doubling the concentration would actually have no effect on rate. So if I go ahead and raise this to the 0 power, you can see that rate gives you K. And if I want to do it mathematically and I go ahead and double the concentration on the inside and still make it to the 0 power, you can see that this whole thing turns into a 1, which means that the rate is going to equal to K, which we already know is a constant. So there's no change in that. On a first order reaction, you double the concentration, it also doubles the reaction rate. Now understand that this is actually a ratio. So again, if you basically have the same ratio, for in other words, a 3 to 3 or a 2 to 2, that's still considered to be a first order. So as an example, if I put a 1 here and I make it into Kx, your rate's going to be Kx. Now if I double this, you're basically going to get a 2 times the rate. So in other words, you can always pull this out. So if the rate triples, and sorry, if the concentration triples and the rate triples, then obviously you know that you've actually had a first order reaction. And so again, doubling the concentration is going to double the rate, tripling the concentration is going to triple the rate, quadrupling, and so on. Now on a second order reaction is going to be the same thing. The only difference now is we're raising it to the second power. So here, if I double something, it's going to quadruple. So if I go 3x as an example, then it's going to be 9 times. So you're basically doing is basically sticking in a number here that's going to multiply by itself, and then you're going to get that quadrupling. But you really want to look for the exponent. If you put a 4x here, let's say you 4 times the concentration, then 4 times 4, if you go 16 times, would still be a quadruple. So just make sure you guys are aware of that situation. Okay, now the overall reaction for any sort of kinetics is going to be rate equals Ka m times b, and the order of the reactions when you add m plus n. So if I'm adding that reaction and I'm asking you is what is the overall, what I'm really doing is adding those exponents. Okay, now here is the section for the rate constant. And the way the rate constant works is that depending on what order of the reaction it is, either 0, 1, 2, or 3, you're basically going to have different rates for those. So on a 0 order, you have a K. First order, you have S seconds, -1, and so on. So make sure you kind of write those down because in each of those cases, what you're going to have is a situation where you get like a third order. So third order, usually I don't see those too often, but you know they can show up. So if I put a 3 in here, it's 3 times 3 times 3, which is going to be 27 times. You know, if you go 3 times, it'll be at 27. So that's going to be a very high number for a third order. All right, so here's an example of, and so the first thing we want to do is we want to take a look at the rate law. A very classic problem is they usually give you an equation, and then they ask you what is the rate law, what is the rate constant, and then the overall rate of for the reaction. And it will give you obviously 3 experiments, each with its initial rates. And so the first step is to take a look at this. So when you're taking a look at this equation, what you really want to look for is how are these things changing as you're increasing or decreasing either of these reactants. So the first one, to find the rate law, what you're going to do is you're going to use the equation of rate 1 over rate 2 equals to KNO1 and N1 H2 M N1. Now what this does is that it sets up the first reaction over the second. Now a couple of questions came out is, does it matter how I flip this? And the answer is not necessarily, because they're still ratios, but I always want to keep them as whole numbers because that way it'll be a lot easier and cleaner to figure out what the exponent is later down the road. It just really depends on your math portion. So here's an example. We know that NO and NO2 is what we're trying to find because the H2 is going to be what we're keeping constant. So you always want to make sure you keep one constant that doesn't affect the rate so that I can see what the rate order is. So because in reaction 1 and reaction 2, H2 is 0.3, we can kind of cancel this number out. We know the K's cancel, and so that leaves us with 0.2n, 0.1n, and then that gives us a 2n equals 4. And the answer here is it's a second order because if I want to find out what the n value is, this will be a 2. Now for reaction 3, it's a little different. And the reason why is because reaction 3, again, we're getting those decimal points, but again, the idea is still the same. Here, once we do that, we find out that if we find 0.67 equals to 0.67, this has to be a first order, because if I'm increasing or decreasing H2 by half, you're basically, the rate's going to go up by half as well. So this is going to be a first order reaction, because again, you're not really, the rate's changing at the same proportion. Okay. All right, so to find the final rate law, what you're going to do is you're going to put the 2 exponent in there for a second order, and then for a first order, you're going to leave it blank. But you do have to put first orders in. 0 orders will not be put in there if there is. And then you finally write rate equals K NO2 to H2. All right, to find the rate constant is pretty straightforward. You're going to take the rate and you're going to divide it by the concentrations of N2, H2. And then what you're going to do is use this data from any of the experiments, 0.09, and let's say we pick experiment, whatever that is. And then we go ahead and use our rate law, we can find that the rate is going to be a 7.5 -2. And I already know it's a third order, so you should have that going in there. The reaction is a third order because you add the 2 and the 1, that gives us that, and then we've got the 7.5. Okay, well that concludes this portion.